Welcome to the next in our series of NASA cross-divisional conversations. We are referring to our initiative as NASA XD. Our evolving tagline is using the principles of public engagement to engage and strategize with the professional scientists that NASA fund. The vibe we're going for is the sort of conversation you might overhear in a conference bar, unapologetically highbrow, freewheeling scientific conversation. Our audience is intended to be the community of PhD educated or equivalent scientists who are funded via NASA programs such as NASA Roses. But we also hope that it might be a place that any scientifically literate or interested person would land to get a feel for how NASA scientists conduct our conversations, a place to set a good example of the best of measured, informed, data-driven debate. Our topic today is designed to help motivate research on whole atmosphere modelling, both to help us to understand the current landscape of those efforts and what more is needed in order to address the challenges that humanity faces as our atmosphere is changing and as humanity moves into a future that is increasingly reliant on space-based assets. This is the third in the series, and our approach is evolving. For this event, we have provided 3 primer talks, which you will have received in the invitation to the event, as well as working with cohorts of student observers from the US and Mexico. You don't have to review the primer talks in order to follow along today, but we envisage that you might find them particularly useful to go back to look at based on some of the topics that we will explore during today's conversation. Today, we're using the example of a subterranean volcanic eruption to motivate our conversation, and our guest is the lead of a mission that made dramatic observations of that event, Dr. Thomas Immel, a physicist from UC Berkeley and principal investigator of the ICON mission, the Ionospheric Connection Explorer.
So Dr. Immel studied physics at Knox College and earned a PhD in physics from the University of Alaska in Fairbanks. Like a lot of good ionospheric physicists, you have to do something in the polar regions. He's co-authored over 200 publications, and his papers have been cited almost 6,000 times. Tom was an early pioneer in exploring the connection between Earth's lower and upper atmosphere. And this event has been organized as a collaboration between the Earth Science Division and the Heliophysics Division, as well as with our wonderful intern cohorts who are online and have helped every step of the way, including helping us with a new initiative for this event, which is that we've got 2 groups of student observers. So this is, I don't know if I hope some of you have heard of the H2O event initiative that's starting to pair students with mission teams. So this is a version of that where we've got student observers helping us to create these curated scientific conversations. So we have 2 groups who are joining us online today. They've been also participating in some of the organizational conversations as we led up to this event. And they will be preparing 2 magazine-style articles, which will be published on the website along with the recording of this event. So this is a team led by Dr. Nancy Wood at the University of Des Moines Community College, and a team led by Cecilia Ayala at the University Polytechnic in Mexico. Negres, sorry, saying that wrong. All right. All right, so as we kick off, can I perhaps get you to say a few words about how you came to be working on the ICON mission? And this picture was one that was provided to me by a colleague of yours who said, and he thinks that this was the where the ICON mission has perhaps had its genesis and the idea for the ICON mission. So maybe you could just tell us a bit about what we're looking at here.
Yeah, so these are a set of data collected by the Image mission, which was a magnetospheric mission. It launched in 2000. This mic is, I think I can put it down here, relaxed. This was the UV imager that collected these data, which was part of the set of instruments on that mission, which was in a high 7 RE polar orbit. Eventually, that orbit of that magnetospheric polar mission was in the equator, and so it had an apogee over the equatorial regions. Turns out it was right near solar max as well. There's lots of signal coming from the ionosphere. So in the nighttime, you could see what the ionosphere was doing. It was glowing, and this image shows basically what the ionosphere looks like after sunset around the Earth, and there's these 2 bright bands of ultraviolet emissions, and of course that has comparable emissions in red line too. So you can go to the equator or near the equator You go to North Africa with a red imager, with a red filter, and see the same related emission. But of course, from space, you collect data over a period of time. You can see spheres distributed around the planet. And so, so that was that. And what we found was that in this plot, we superposed contours of temperature variations that are driven by tides that originate in the troposphere and stratosphere. And so you can see the contours on it. The numbers that you can see are very few, but there's 50. 50K is the amplitude of this tide. 50K is a huge number, so that's particularly at this altitude, which is, I think we're showing at 115. So it's about a 30% change in the absolute temperature, something like, it's like if the amplitude of the temperature in this room were 50 degrees Celsius, you'd be going from boiling to freezing. So that's the size of the tides, and so it's actually, in hindsight, no wonder that there's a wind pattern associated with these that drives electrodynamics. So this is our supposition at the time, was that there's a wind pattern associated with these tides that drives electric fields in the daytime that produces, you can sort of see in this plot the peaks around the planet. There's several bright areas around the planet. And so this was an interesting confluence when you talk about cross-divisional. This is interdivisional, but really complementary science coming from a magnetospheric focus mission to give us a new view in the ionosphere.
Is IMAGE still going?
IMAGE ran for 5 years, and like ICON, it just quit one day. December 18th, 2005.
And if IMAGE had been in orbit doing the similar thing when the Tonga volcano went off, would this picture have been disrupted in a similar way to what ICON saw?
We have okay, we're getting way ahead of things, but we have a lot of questions about what happened to the ionosphere regarding in the time of the Tonga volcano. And one of our questions is so if you go above the ionosphere, you keep going, you end up into even lighter ions, and mostly hydrogen and helium in the plasma sphere. And it generally co-rotates, it's not stuck to it co-rotates just like everything else, but on magnetic field lines. So how much of the plasma sphere was drawn down by basically the huge reduction in plasma densities in the ionosphere? This is a question that...
You're positing that because that's the sort of process that would have had to happen for it to then have an emission that IMAGE would have seen equivalent to this.
IMAGE had a plasmaspheric imager.
Okay.
And it may have been able to, depending if it was at the pole or the equator, inform us as to if there was some effect in the plasma sphere, several Earth radii out even, that could help us understand why the sort of the very extreme variations we saw in the ionosphere in terms of composition and things. You'd almost have to reach up to the plasma sphere to pull plasma down.
All right, and I get it. We're getting ahead of it.
Yeah, I know.
We did have, I think, one of the figures that we were talking about earlier. Perhaps this would be a good time for you to describe. So this is some data that was from ICON during, I think you said it was an orbit that's at 75 kilometers, and it orbits once every about an hour and a half. So each one of these numbers corresponds to one of ICON's orbits during the day of the Tonga eruption. So do you want to talk us through a bit more about what we're seeing there?
Yeah, so let me back up a little bit. So ICON's in a 27-degree inclination orbit. So its orbits on this plot clearly are captured between plus or minus 27 degrees. That's where it's taking sampling. And these data are from the in situ measurements on ICON. So we have remote sensing instruments that are generally looking north, but these are all right in situ. The orbit is 575, so 575 kilometers.
Oh, 575.
Yes. We have to be way above the atmosphere to stay on orbit, so that's all right. So as satellites go, these orbits go from left to right. So we would be entering in this scene. If you could see the scene as it developed, you'd be entering from over here by the Philippines, and orbit number 1, which is labeled with the number 1, would be tracking down towards lower latitude, crossing the equator and tracking down towards lower latitudes into the southern hemisphere, and then back in the northern hemisphere on the part of the map that you can't see. So I forget which.
That's the red triangle.
Okay.
Red triangle's the eruption, and then
the red triangle is the location of the Tonga volcano, and there's concentric circles drawn here of distance. So those are, I think, 3,000, 6,000, and 9,000 kilometers from Tonga. That's, I guess, or am I dropping a hint that things were propagating away from Tonga? We have some.
Well, I don't know, but before you get to it, because I think that's one of the things that we know, having looked at it, and when you described it to me, and I get it, I was like, well, once. Yeah. And I can only imagine what it must have been like when you saw it for the first time. But actually, we don't have a baseline yet. So describe like orbit number one, like what you would normally have seen, in inverted commas.
So orbit number one, so this was in the afternoon in Tonga time, and so noon is over Australia or something. And orbit one is a plain old on this time series, a sort of a slowly varying plasma densities along the orbit that are just indicated with this sort of pink and red color bar. In orbit two, everything has changed. Orbit two is about an hour after the eruption, and what's remarkable is to us as we looked at these data is, okay, there's no way any of the waves from, first of all, you see the eruption, you imagine everything just sort of this towering plume of smoke and ash. That whole thing, that plume was full of water, millions of gallons of water. And all that water that had vaporized was condensing. And when you do that, all that condensation, you're releasing a ton of heat. And so it's sort of a way of transporting all this heat energy from the volcano up into the stratosphere. And all of it's condensing, and it drives large atmospheric waves that propagate away from the volcano. So, basically along these concentric circles. But that was we were there. So when I saw this orbit, I was like, oh, we missed the whole thing. And then I saw the data. It said, no, we didn't. We saw something happen.
And you say that because
because
you saw what ICON were doing, and you assumed that the residue from it would be gone by the time you got to the later orbits that were getting closer to it.
I assumed that you'd like to be on orbit 4 when the volcano went off, and not over there by Hawaii.
But it's still only 6-7 hours. Is that 1.5 hour orbits? Is that what you said?
Yeah, so it's about 3 hours later.
Spacecrafts are crazy.
Yeah, well, I felt that we'd missed it. I felt that, and but in fact, within an hour of the eruption, we saw effects much farther away than the waves could possibly have gotten. So this goes right to what ICON was built for. ICON was built to understand electromagnetic connections when the lower atmosphere interacts, drives waves into the lower, across the boundary of space. It can create electric fields and drive currents that then, in this picture, we explain this by understanding that there's the magnetic field of the Earth connects Tonga, basically. If you follow a magnetic field, go up the magnetic field line from Tonga, you end up coming down in the northern Pacific. And that, so you see along orbit 2, there's this enhancement in densities, and then a sharp reduction in densities right next to it. And so this was explained in the paper by a PhD candidate, Claire Gasquet at Berkeley, showing how the expanding wave from Tonga was alternatively forcing plasma densities up and down much farther away from the volcano than the waves could have done if they weren't generating this electromagnetic effect as well.
So literally neutral particles emerging into the atmosphere from the volcano are sopping up all the plasma that exists at those altitudes. Is that a way of thinking about it?
Neutral particles are carrying momentum that's into a generator, into an electric motor that exists, sitting there waiting to be energized by something. And if you carry 200 meter per second winds up into that motor, which is, what was that? 200, I looked it up. 200 meters per second is, oh, well, that's 2 football fields a second. We were supposed to convert to things that people know to miles per
I
hour.
that in my thesis just to make sure my advisor was actually reading my work, like trout per furlong or something. Right.
But everyone knows a football field per second.
Of course I do.
We're fine. So, and
Aussie rules, British soccer field.
It's like the same. So at 2 football fields per second are the winds that are coming, that are being, we understand, because you can read off the electric fields that you observe on orbit number 2 and say, that must be generated by winds that are this big over Tonga. And then you can go run your whole atmospheric model and see if you're right, see if your model is actually producing that.
I don't know if I quite got it from that though. So, because I love the idea of it ripping off the ionosphere or throwing it off into space, but I suspect that that's not quite the right way of thinking about it. So is it that it becomes less ionized?
Well, we imparted, so how did it get less ionized?
Yeah.
That's the topic of this next paper that we're working on, and is a topic of papers that are in press right now. We've seen in press people are working, like, where did all that plasma go, and why did it go away so quickly?
Before we get on to more of the scientific details. So one of the things we talked about that I really enjoyed was we were talking about would you rather be a student now or a student when we were students back in the day? And so can you tell me a bit about why you thought what Claire was looking for? You were talking about she was looking for the smallest waves and how, because she's in her 4th year now, right? She's just entering her final year or doing her pre-defense.
Yeah, she's good to go. She just needs to write her thesis.
Right. I guess you should just repeat a bit about what her trajectory has been like as a recent student.
Well, I think that there was your first question was, would you rather be a student now or before? I like being a student before, because I had a VAX and the internet was like typing and stuff, like there was no internet and it was a whole new thing. So I like having been there when the internet, you had to figure out what in the world it was. But scientifically, I don't know. Claire's working on that paper still, which is looking at waves that ride the terminator. Terminator is where the sun's setting and the sun's rising. And I think in some of our first studies where we had to look really hard for that wave, she was showing that, sure enough, it's there. And it's actually the sunset terminators even, it's got this stronger wave than, I always thought it'd be the morning terminator, but in any case, it was very interesting to find this, and we're making great progress in this, and then this volcano blew up, and to go on from there. And the work continues with all of our data products for that are in situ, and the wind products, which we may not get to. But.
I'm guessing she had to extend the color bars quite a bit. Like, it was looking for tiny little waves.
Yeah, we were looking for 5.
Yeah, now we're looking for 100.
Yeah, and then we were presented with 100.
Yeah.
So it was quite, but yes, we had the tools ready to go, and so she was able to write a paper, an early paper, as well as Brian Harding on our team as well. He was looking at currents, which we didn't carry a magnetometer on ICON for a number of reasons. The resources, we were pretty resource constrained, but SWARM carried a magnetometer, and we had some conjunctions with SWARM, an ESA mission, which is right in our ballpark of this area of study, and but they had a great measurement from their magnetometers that we were able to compare to our winds.
ICON doesn't have a magnetometer?
Don't carry a magnetometer.
Did you want a magnetometer? Maybe didn't need one.
We didn't think we needed one. We weren't specifically looking for electrojet currents. You know, the magnetometer signal here is going to be the equatorial electrojet.
Yeah.
Auroral scientists understand that there's an auroral electrojet. There's an equatorial one as well that exists right at the magnetic equator. It's this interesting phenomenon. And it's related to what's going on in the plasma overhead. We're measuring the plasma overhead, what it's doing, and by, in some sense, deriving an electric field that's associated with that motion of the plasma, the E cross B drift, if you will, in plasma terms. And so we didn't think that we needed the magnetometer. Plus, you've got to keep everything magnetically clean, and we were steering our spacecraft with big magnetic torque bars. So there were some differences in opinion on whether, in the end, we didn't fly a mag.
Okay. I'm a bit of a fan. Yeah. Well, I suppose, yeah, it's always a tricky one with the fan.
It helps when someone else flies it. Like, for instance, in the future, GDC's flying a magnetometer. I can think of some things to do with their magnetometer with another mission that we could fly alongside it.
Yeah, imagine it like a service laboratory so that everyone else can key off. Yeah, I think that's probably exactly what they have in mind, hopefully.
Mm-hmm.
I think you gave me some more figures, which I want to give you a chance to talk to.
Oh, yeah.
I'm sorry, I tried to put that back on a white background, but I failed.
Well, it certainly kind of makes the point.
I think we got into disco mode a bit early.
It's fine. It shows a wave propagating around the planet. So, I mean, what I think a number of people who are familiar with this event at all, or big volcanic explosions, is that these things have effects that propagate completely around the planet. And this one is not unique in that respect, but it certainly was prodigious. It produced a significant wave, which in the lower atmosphere, the properties of the wave are described by one Professor Lamb, and LAMB. So it's a Lamb wave. It moved at I think, exactly the speed of sound, and it's pretty much vertical, like as it's propagating around the planet, it's just straight up and down. It's not tipping forward or tipping backwards, or it's a very well constrained wave in the troposphere. What we found is that there's other waves associated with this thing, particularly gravity waves, which are not Lamb waves, which have a much different dispersion relationship and move in the thermosphere much faster.
So take a stab at talking us through the fact that it was observed at Hawaii, but faster than it could have got there reasonably.
Oh, well, it goes back to the electromagnetic connection. Like the waves that propagate out from, if you think of the magnetic field as a conducting wire, which is in some sense is not a bad analogy. If you hit that wire, it's with an electric field. You know, how long does it take when you put try to run a current through a wire? How long does it take for that current to get to the other end?
Electrons are basically photons.
It's pretty quick. So it's actually it's an alphanic propagation. It's probably an alphane wave, which is doing the work of carrying that energy when you just perturb the magnetic field by driving a current locally by pushing plasma across a magnetic field line, just like an engine or a motor. That wave is going to move at approximately 3,000 to 6,000 kilometers, 3,000 to 6,000 meters per second. So what's that? 30 football fields to 60 football fields per second. So the wave is moving at 3 to 4 football fields per second, and the electromagnetic energy can just get there much faster and drive changes in the ionosphere right away. You don't see the same thing in the neutrals. You don't suddenly see the Lamb wave or whatever wave it was driving the motor in your vicinity, although you certainly are seeing a reflection of it in the plasma. You can see, if you could have imaged that whole region of the plasma where the foot point on the other end of the field lines from Tonga towards Hawaii, I'm sure you would have seen the expanding ring of just a mirror of electromagnetic mirror of what was happening in Tonga over by Hawaii.
If we'd had another icon doing that orbit, I guess it would be. Is the reflection strong enough that you'd have seen it? I guess it was so strong an icon that.
Yeah, it would have been nice to get. Yeah, sure. If you had a couple observatories in that similar plane, you could have seen some of the structure coming from Tonga that we saw in a one slice. So it would have been, or you could at least seen a time series of the change, the expansion of the wave. In essence, we did see the time series. We showed up 90-some minutes later and had shifted westward.
Mm-hmm. So, and you said that the other volcanoes, were there no other volcanic eruptions during the icon era? Have you gone back and looked to check? Like the one that
of course, you think about it.
Iceland volcanoes, they're going off every 5 minutes. Was that not in the last few years?
What did I miss?
Yeah, maybe we should go and check. Quick, get on the Where do we get data from these days?
No, I mean, the corollary for this one, and the one that put us,
It's going to move on to the next slide.
think right away, is the Tohoku
I
earthquake.
did have a white version. Sorry. Continue.
Oh, look at that. That's a little better. Okay, so two things we thought about. The Tohoku earthquake happened in 2011, and that had enormous effects in the ionosphere. It was my first. I was sort of shocked to see how big those effects were. It was quite a different event. You know, that Tohoku, it was a very different atmospheric driver.
Okay.
You know, there was no giant water vapor condensing in the stratosphere. It was all surface, and that surface was didn't just move once. It was constantly going up and down. So that was different. This shows where the land waves, waves converge. If we get to the slides, right over Morocco, over Western Africa. So if the waves were symmetric like this, which in fact it's hard to imagine they stay symmetric, but in this simple picture, those waves are going to have combined to have an enormous effect on the other side of the planet, which in fact they did. It's pretty interesting observations by the Gold Mission. The MIT group published that. The Haystack group and Urcha published that paper talking about the extreme effects on the equatorial ionosphere. Because, you know, Tonga is near the equatorial ionosphere, so the antipode is also near the equatorial ionosphere. So it twice had remarkable effects. Mm. And in the other hemisphere, it also erased the ionosphere, really reduced plasma densities very rapidly. It's pretty interesting.
Okay, yes. So the magnetic latitude of the volcano, the Tonga volcano, was rather uniquely positioned compared to perhaps those other ones.
Yeah.
We'll move on. What we got to the next one? Because I know this isn't your specialty, but I do want to invite you to pontificate a little bit about the state of whole atmosphere modelling, what might motivate it. One of the things that I think I've learned as we've been having these conversations is that in the neutral atmosphere modelling, which is kind of born out from the Earth Science Division, kind of that goes up to like maybe 50, 60 kilometers, at which point you become partially ionized, and the science moves into the heliophysics division, mm-hmm. which is one of the reasons that we chose it for a cost-divisional event. And the observation, you know, that if we want to solve the problems that humanity is creating for ourselves, that we may well be needing a joined-up model. One of the things that from the Earth Science modelling point of view is that I think they recognise that their model is often used as an input and is needed to be used as an input for us to understand what's happening in the charged regimes above it. But I wonder if I could get you to speculate on what processes or the need might be for having a whole atmosphere model that goes from mud to sun from a neutral atmosphere point of view. What is it that happens at your, in inverted commas, altitudes that might affect the neutral layers and the layers below it that would help us to motivate people developing the Earth, the neutral areas of the Earth's atmosphere models to look at how the feedback with the ionized layers might affect
So I think two things. Just historically, you know, the upper atmospheric models were never coupled to the lower atmospheric models because it became more and more computationally expensive as you went down, and the lower atmospheric models just kept tried to do as much as they needed to until to make predictions that were necessary. But they kept finding that, okay, we have to include the stratosphere, okay, and mesosphere, okay, let's go. We're in it pretty soon. And we were finding the same thing in space. So eventually the computationally more difficult problem of weather and with new resources, we could reach down and basically touch the weather models. And then suddenly, I mean, that's when those discoveries were made. The first slide you showed was a confluence of events, that the upper atmospheric models were finally integrating effects from the lower atmospheric models at the same time we were taking images of the ionosphere like we did. It was a remarkable confluence of events. Let's see. So I think that the dynamics of the upper atmosphere and stirring the upper atmosphere and doing these things, not necessarily with a volcano, but say a geomagnetic storm, is usually going to come, in my understanding, chemically. And the important changes that you could get in the stratosphere, and I think have been shown to get in the stratosphere, can propagate down from the polar regions during really, really large geomagnetic storms. And this is This has been a long field of interest, and I think in the last around I think it was at the Halloween storm or something. It was 2023 storm that we all talk about in the field, or the related storms at that solar maximum. Produced some really large changes in nitric oxide, which was seen to descend in the polar regions down through the mesosphere and approach the stratosphere, if I recall. So, and so what are the climatic effects of that? And those are open questions, I think, still. But yeah, I don't see that. I mean, we don't see winds generated by the aurora that we would, you'd have to call off a picnic or something like that.
No, I see that, and I also think that the what you're getting at there a little bit is also we just don't know yet. But every time we add another layer to the model, we learn something new that is important, and that we, with hindsight, recognise it was important to include. All right, thank you.
I think that's right.
We didn't talk about what we were looking at here, so do you want to tell us a bit about this?
Well,
and
this
as I
is just-
predicted, time is marching on, so I'll just, before we start...
I think 24 hours after the volcano, I mean, this showed up online, and the groups that were or tasked or working to image the Earth just did some difference images to show that, wow, yeah, in the infrared, the radiances that we were seeing on Earth, which are often affected by the difference images show clouds moving, shows also a giant wavefront moving across the scene, and that's generated by the Tonga volcano. And so this was the first idea that we had that we should go look at our data.
Oh, is that right? That is beautiful. So what do they make these different plots as a matter of course, or did they do this because the eruption had gone off, and maybe this is something they need to start doing as a matter of course?
I think obviously it has some useful quantities. I mean, you could see anything that was propagated up. You could see a small volcano with this thing, right? I mean, that's an obvious signature. So there's other things that could clearly be seen here. I think maybe like a typhoon or something may have waves emanating from it or something.
That on my screensaver. It's like the modern day SETI or something where you're just always looking at that. It's amazing. If they were to, if they could increase the contrast to like what God sees, like an ideal event, do you imagine that they would have also seen the reflected wave then? Or is that uniquely on a spherical effect?
Yeah, I don't think the reflected wave was going to get down past the ionosphere. I think that was an electrodynamic effect, and that's where you'd see it, and then there's some driving, but I don't think, again, you propagate. I don't see it.
I don't see it either. All right.
But we could ask the Lowell people what they think.
All right, what else have we got?
Oh, well, what did I bring? Slide.
Oh, I do. I would like to have a chance to show this if we can. I did have trouble getting this to run
So
before.
this is courtesy of Sharon Battis and our group. Claire, part of our group, put this together. This was winds at 150 kilometers driven by the volcano. So again, it's the dynamic effect. What you saw propagating out in the infrared has a corollary way up at 150 kilometers, and so says the model. And this model is run after the fact with inputs. I forget, the paper cited here describes specifically what they did to couple lower atmospheric model to their wave model and to carry waves into space. A couple of things here that are interesting. Obviously, it has different characteristics in the direction of propagation, which come from a number of forces, Coriolis force, and other things that may be affecting the propagation. But it sure is useful in comparing to, because this is right in the dynamo region. These winds are the ones that are driving changes in the ionosphere over Hawaii in our first pass from ICON. And what I still think I need to see, we're going to work on this, is to get specifically a prediction of these winds from our observation and compared to their exact winds at the foot point. It's not pretty exact science. Like, we know where the field line should be mapping to, notwithstanding any perturbations. The ICON track goes, the top half of this picture, but very close to Tonga. So we can make those comparisons directly and see, is the model right?
Yeah.
Does it have the right size waves?
Yeah, that's beautiful. So say again, there was Vedas. Where's that team based?
Sharon Vadis at Northwest Research. I think that's right. Sharon, sorry if I'm wrong. Is an expert here, and as soon as the volcano was an event, I think started working on this modeling just like we did.
I want to ask you a bit about, we'll come back to that, a bit about the human element of your team, and how perhaps you could talk a bit about how COVID affected your team, and I like to make sure that I think before we get our scientific discoveries into a textbook that can be taught in schools, most of the scientific discoveries are really human stories, and I think that's one of the things I've been most enjoying about doing the NASA XD kind of conversations. So most of the discoveries are really discoveries that have got human stories behind all of them. So how did your team, I guess, pre-COVID, like anything that you have done that you enjoyed, that you could say was a thing that worked well, and then in particular, like how you coped with the lockdown and anything else about that?
I guess a couple of things happened. I mean, COVID, everyone ran off, started working from home, and we're finding out how efficiently they were able to do that. And I think it varies from person to person. Some people had a very difficult time with that, and some people was like, finally, this is how I've been wanting to live my life. The benefit that we got from COVID is like, okay, I finally have to organize with the undergrads to have one-on-one meetings, or I'm never going to see them. So we set up Zoom meetings with each individual undergrads. Suddenly I had office hours, several hours a week with undergrads, and suddenly we were getting a lot of stuff done with undergrads.
Mm-hmm.
So that forced us. So in the end, there was a benefit to that, and a realization that this is what you should have been doing all along.
In a realistically manageable way for you, for the people doing the online meeting.
You mean who was it? Was it manageable?
Yeah.
Was it just too much? Well, we'd have three. Well, I don't know. We had 3 or 4 undergrads at a time.
Okay.
So I thought that was actually an eye-opening thing that we were getting. One of our undergrads just published her paper, and she's graduated, but she published basically our first geomagnetic storm paper, analyzed all these data, and so that came. I haven't. As much as we've talked about it and it's worked in the past, I haven't published with a senior Berkeley undergrad for a while. Mm-hmm. And I think we've got another one coming. So another paper that was, again, started off in the middle of a pandemic, which was an awful time in a number of ways. But that's the thing that stands out to me, is that it forced us to do the things that set up the meetings that you always thought you'd have, but you didn't find time for. Okay, I actually have to make the time for it and put it on my calendar. That's the other thing, is the calendar, and everything's on a calendar suddenly was, I don't know, did you have that experience? Your calendar suddenly became more important, or more?
I definitely feel to this day that I'm sort of led by the nose by what's on my calendar.
Yeah. Is that did that happen during COVID, or was it before that?
Pre-COVID, I was in the situation of I would choose which of the 3 meetings I could attend, and everyone would assume I was somewhere else. But actually, after COVID, everyone knew, where everyone was. So it's not like, oh, she's probably in the other room. So I suppose, yeah, there was an element of needing to be more realistic about what I can achieve.
A lot of things you forget.
Yeah.
I'm already, here we are. Is anyone wearing a mask? Oh, someone's wearing a mask.
Yeah.
Maybe they should have a mask on.
To us. Maybe we should have been wearing masks before COVID. Actually, I think that there's an element that we've learned that wearing a mask in public isn't weird anymore, and so I think a lot of people are just going to keep doing it no matter what.
And it's fine.
Yeah, right, and that's fine. And I think that's also something else, right? That there's a new tolerance of all sorts of different things. Like I really love that we're doing little badges when I go to conferences about, are you a hugger or not, basically. So I know not to, molest people if they've got the red thing around their neck. And there's been a lot of those kind of human conversations that have been really meaningful and good.
Huh. Okay.
I want to ask you, and people online, if you've got any questions, could you post them into the chat, and we might open the mics as well if we can do it reasonably with the amount of people online. So right back to the icon. So I know icon has stopped transmitting. Is it going to deorbit? What will happen? Is it going to float around? Can we go and visit it one day when we're doing suborbital?
We could go shrink wrap and bring it back and find out what happened. We'd have a better handle on it if we did that. We don't really know. I don't think there's going to be a firm conclusion on which part failed, but it focuses on the avionics stack. No, it was working extremely well, one orbit, and the next orbit it wasn't talking to us, so it was sort of a surprise.
That aside, if you could do icon again tomorrow, is there anything you do differently? I said No,
this was a good question.
That's a good answer.
Actually pretty good.
Yeah, that's a fair answer.
I mean, okay.
I built two.
I wouldn't, maybe. We flew the flight spare for the IVM instrument, which gave us an innovative way. Our fields of view were looking north, and we had one instrument collecting plasma, and that was what you had to do. So we were always looking north, and we had one instrument collecting plasma in the RAM direction. Couldn't do it. And let's turn it around because we put our flight spare of the drift meter there as well, so you could look south, and I would have looked south more. Because we could reach into the South Atlantic anomaly, which is sort of a no-go zone for us. The detectors get flooded with radiation, but we could have seen more there. We tested it out. We know it worked. We had the second IVM working, but we didn't. The mighties are thermally sensitive, and they take time to settle down. The wind instrument is thermally sensitive, and so it takes about a week to settle. And so they didn't like my ideas of flipping the thing back and forth all the time.
And you always think there's time.
I'd flip that thing. I want to have a better look at South America.
Yeah.
We did some conjunctions with Hikamarka. We did some winds at Hikamarka, but the baseline of the winds were drifting on. The thermal environment hadn't quite settled down, so it's harder work to analyze those. Either that, or I wouldn't have flown that flight spare. Just kept it down here, so now we have a flight spare to fly on the next mission.
I love it. All right, well, thank you very much. I will give Tom a round of applause for those in the room. People online, please navigate to your little clap hands and give Tom a round of applause. And then, and some time for a few questions. So we did put some mics in the room, and if you don't mind, I'll repeat it if you want. Okay.
Okay, thanks, Thomas, for the nice discussion. My question is, when you say the depletion in the ionosphere, is it because of the Tonga effect, or is it convoluted with some geomagnetic storm effects? So I was not sure if there was a storm during that day. Yeah, thank you.
That's a good question. There was a big geomagnetic storm that day, and that made it sort of interesting. A couple of things. So why we explain these effects as volcanic is because, for a number of reasons. If you look at Claire's GRL article, we have a baseline for the drift, and then we have where the drifts were when the volcanic effects were observed, and they're quite different than the baseline. The quiet time baseline and the drifts are very different already. So we're certain that we're seeing geomagnetic effects. But then the Tonga effects are so obvious, I invite you to look at the Gasquet et al. Article from 2022, the GRL. It shows an extremely clear signature of concentrically radiating wind field in the E region as detected by a remote sensing observation magnetically conjugate to it. It really works out well. So you should have a look at the paper. It's on our website for free, I think, if you can't get the GRL. I think you can get the GRL.
Yeah, thank you for that question. That's a really good point. So there was a geomagnetic storm going that day, and when you say you're confident the effects are volcanic, it's not just I believe, it's a there's no way that could have happened just from the geomagnetic storm. Is that right?
Yeah, geomagnetic storms don't do that. Geomagnetic storm does exactly what you see in the data until you hit the volcano.
Right.
And then the winds around the planet are so much more energized by the volcano than at least in our range of latitudes that we're sampling. You know, in the auroral region, you could have very large winds or whatever driven by a storm. But at lower latitudes, clearly the volcano is the winner. I mean, you saw Claire's talk. So Godzilla versus King Kong, and there's a clear winner, at least near the equator.
Thank you.
We have one more from Diran. He said, what altitudes are the wind modeled?
Oh, this was at 150 kilometers. I mean, the winds are, so let me be clear. The wind model is continuous down to lower altitudes. This is just a slice through the model at 150.
I don't want to play for it again, but I guess that answers the question. Thank you.
Yeah, sorry.
All right, I want to give you a chance to talk about this one, but before and it does play very slowly, so maybe I'll just let it play in the background while I'm asking you a different question.
Okay.
To get you to talk a little bit about the state of the scientific conversation, in your opinion, and I guess in general, like throughout your career, because I see that that we have the traditional places where we go and have our conversations. The community's got bigger and bigger. It takes longer and longer to get to the cutting edge. I'm slightly concerned that we have people doing exactly the same physics in two different places. Like increasingly with exoplanet analysis, we've got people doing atmospheric studies who are, hopefully not recreating the wheel, but they're doing similar things as we've been doing the Earth's atmosphere for hundreds of years. So, yeah, can you just talk to us a little bit about what you think about the state of the scientific conversation, how we're organising ourselves with respect to conferences, and if there's anything you'd like to see done different?
That's a good question. The effect of stovepiping and how you end up not having these intersections where you can actually find out you're doing the same thing as someone else. Well, let me try to think. Like, what I'm curious of how important this stuff is to anyone else in, say, planetary. Do you care what the tides are on Neptune or Uranus? Why not about Jupiter? What do the gravity waves emanating from the Great Red Spot, this giant typhoon on Jupiter, what do they have an effect on the upper atmosphere, and do you guys care? I've never had those. I've had two exchanges with two scientists probably in 2 decades one was about Jupiter, asking if there was a pre-reversal enhancement that drives these equatorial plasma bubbles that you're seeing on the left-hand side here. And the answer was, I don't know. What does the equatorial ionosphere on Jupiter look like? Yeah, not sure. And I'm like, I am so interested to know that answer to that question, and so I'm just not sure that my interest goes. Be interested to know if there's interest. I mean, that's basically what it is. Could we do an equatorial mission? Could we do a 27-degree inclination mission to Jupiter? Where is our South Atlantic anomaly is over South America, and that's where all the radiation belt particles sneak in. Where is that on Jupiter? Because I want to plan a mission with Starship to go near the equator of Jupiter, but what inclination do I have to go? How high an inclination can I go to avoid? There must be a spot on Jupiter where the radiation belt particles precipitate more than elsewhere, and you clearly want to avoid that. It's the worst place in the solar system for radiation. So
there was a wonderful talk by a student of Tom Stallard's at the Outer Planets Assessment Group meeting this week, which I'm going to dig out and send to you. And they were talking about things which are very much related to that. Certainly associating an equatorial darkening in the ionosphere with a H3 plus depletion or enhancement, and then a number of other regions which they'd also associated with something equivalent to a South Atlantic anomaly.
On Jupiter?
Yeah.
Oh, good. I'm glad I came out here.
Yeah. So, yeah, that's some wonderful data coming out from. I'm motivated by the Juno mission. I'm not sure I think that was telescope data.
Wow.
Yes,
Wow.
right. But it's interesting though what you say. Of course, everything is very interesting. But there's that we look under the lamppost. We look at what are the things that we're able to study because of the things we've launched. But it is the more we launch, the more we're able to study. So I think the more that we're having more assets at other planets, the more we're seeing that we've got something more to bring to the conversation, and there'll be something new to be learned, I expect.
Pretty sure this in-person meeting was the way to go, not some online thing. Be like, bye-bye, so we can go talk about this more.
I think that might be a failing of mine, because I do think I don't engage as much when it's online, unfortunately, and I suspect I'll say it out loud as a mea culpa, but and also to forgive everyone else online who has the same problem, because I do think when it's in person, I'm much more likely to be engaged.
I totally understand.
Yeah. All right, the last few minutes, you want to tell us about what we're seeing
Well,
next?
these are images from gold, and these are images.
And gold
is a UV imager, just like the first images we saw from image. It's the same emission. It's 1356 is what they're looking at. It's an oxygen emission. You get it when there's a lot of plasma, a lot of oxygen plasma, which is what the ionosphere is made out of. And on the left is the scene as gold follows the terminator, as the sun sets, as the planet rotates, and gold is on a geosynchronous platform. It watches the night side, and you can see this big aurora up there. That's that geomagnetic storm going on. That's effect that SAS asked us about. There's significant auroral activity.
I presume that bright line in the bottom corner is
that's the day side.
Oh, that's
the
where
terminator.
That's in sunlight still. Okay.
Yeah, that's just the sunlight of the Earth. The difference between the before and after is before the equator is split into these two bands, just like we know from the average images from image or anyone else, and it has all this interesting structure. But look how these images start about the same, and then the wave gets there. So this is exactly the time of the arrival of the wave from Tonga, 17 hours after the eruption. And you can see the difference. It looked like it was about to be the same ionosphere, and suddenly that wave showed up and just erased everything. Just smooshed it really well.
And I think I know that like a day or two later, everything as far as we can tell is back to normal. But is the stuff that was lofted, are those greenhouse gases? I mean, is it done as a favor or is it worse? Anti-greenhouse gases, if there is such a thing.
So lofting, you mean the volcanic?
Yeah, whatever.
Well, so this whole thing is coming from lofting, right? I mean, at the equator, you're lofting plasma in the daytime. These winds are driving electric fields or whatever you will, like currents, and it tends to lift the plasma, and then it falls back down the field lines and diffuses back down the field lines, and it parks it right there. So there's a question of how you actually erase plasma at nighttime. How you erase it ever. You need to really do a significant amount of work, and it looks like it's really a dynamic effect where you're really causing a dynamical, what should I say, a much stronger reaction between the neutrals and the plasma to neutralize the plasma, to recombine it. But you said greenhouse gas. I don't, do we have effects of the volcano in space that aren't dynamical? I'm not sure we've got there yet. We saw some discussion at AGU in Chicago, where it was announced that we had seen lots of water in space. I'm not sure we can confirm that with ICON's data.
It was announced lots of water in space after the volcanic eruption.
Yeah.
And I think water is a greenhouse gas.
Well, it's a greenhouse gas, but water vapor is a greenhouse gas, but it varies in response to temperature, not the other way around.
I see. The energy was the same. All right. Well, thank you very much.
Thank you. It's been
It's been
great.
an absolute pleasure. All right. Well, thanks. I'll speak one more time. Thank you very much, everyone.